Yeah. Good afternoon, everyone. Welcome to today's session of AEEWI, and wish you all a very happy Diwali. Today is Dhanteras, so wishing you health and prosperity for the complete year. And today we are privileged to have with us Mr. Som Derashree, who is a very well-known personality in energy fraternity, and he has great experience. Let me introduce him briefly, and before we begin. So, Mr. Som Derashree is MD of Saigu Innovators Private Limited, and his company is authorized by the Ministry of Power for M&V audits under PAT scheme, and also authorized by Government of Gujarat for industrial and commercial energy audits. He is international trainer for CEMI, CEA, and CMVP, that for from AEE USA, and PMVA for EVO USA. He is a certified lead auditor for ISO 5001 energy management systems. He is already, since he is a trainer, so he himself is also a CEM and CEA from AEE, and as well as Bureau of Energy Efficiency. He has over 25 years of industrial experience at Grasim Nagda and NPC and Petrophils Baroda, and he has been a vice president projects at Alembic Limited Baroda. He has carried out many international energy audits in Europe, Saudi Arabia, Malaysia, Bangladesh, South Africa, and China for companies like Osram, Arcelor, Mittal Steel Plants, Shell Refinery, SABIC, Tansi, Petrochemicals, ADB, etc. He is working as a corporate returnership on long-term basis with few MNCs and public limited companies to improve their energy efficiency and reduce their personnel at GACL, GFL, Rubamin, Mott MacDonald, Silox India, and L&T, and many other companies. So, and today he is going to speak on pump and pumping systems. So over to you, Mr. Derashree.
Thank you, Bhavnaji. Good afternoon to everybody, and I take this opportunity to wish you all a very happy Dhanteras and the coming Diwali. May this bring you health, wealth, and prosperity to all. I hope my slides are visible. Can somebody confirm? Bhavnaji? Bhavnaji?
Yes, your slides are visible.
And is moving also, no?
Yes, they are moving.
Okay, fine. Thanks. Just wanted to make sure that. Okay, friends. So today we are on a topic which is very important topic from the energy auditor's point of view, and also yes, water being one of the very precious commodity now. So pumping and energy and water both are very, very important for us. Let's see what we're going to cover in this 1 hour session. We'll talk about the type of pumps quickly, some pump terminologies, pump selection process, what is NPSH and cavitation. We'll talk about pumping systems, flow strategies. We'll talk about the energy conservation opportunities in pumping. What are the emerging technologies in pumping? And of course, I will share some case studies for benefit of all. So there are basically two categories of pumps, rotodynamic pumps and positive displacement pump. Let's cover first the positive displacement pumps. We have rotatory types where you have screw, gear, and rotary, and reciprocating type where you have plunger, diaphragm, etc. I'm just giving you some pictures basically for a quick understanding of what the pumps are. Now we have this gear pump. So on the left-hand corner bottom, you will see this gear pump. Basically used for viscous fluids and maybe sometimes a little slurry and other products, resins, etc. We have screw pumps, which is the second picture at the bottom. You would find there are two screws, and the screws rotate and pushing the material forward. And there you have a rotary vane pump, also known as peripheral pumps, where you have entry of the fluid from one side, and then this rotational blades, they take it forward and then push it. This is slightly concentric opening, so the material gets pushed out as it forwards towards this circular path. The reciprocating pump, we all know, yes, you have cranking arrangement, basically piston moving forward and backward. You have a plunger pump. This is a typical picture of the plunger pump that moves up and down and sucks the material here. Then you have a diaphragm pump. The diaphragm pumps are mainly used in, when slurries are required, or ceramic industries, all the sanitary wares, etc., where you make, or even in the mines, big mines, you have pumping, which is a lot of slurry, a lot of solid contaminants. There you use this diaphragm type of pumps, which have no direct contact with the material, but yes, there's the diaphragms which pushes forward and backward, and the pulsating action results in pumping of the fluid. Then you have a piston pump, which is typical of piston. You push the thing forward, and then there's the valve opens and you get the pump outside. You have a radial piston pump. You see the as the central it's a slightly eccentric connection to the pistons. So as it moves, you have suction coming in here, and it gets pumped out from the other side when the piston is in the forward position. So both at this side you have all the suction, and this side you have all the. And you have a rope type pump also, if you have heard of. It's very, very old technologies. Like you have a rope which is turned around the pulley. This pulley is rotated, and then you have those balls which are moving up, and then they bring it's like a bucket elevator kind of a stuff. Not very often used. The second category of pumps we talked about was a dynamic pump, and where you have the centrifugal pump, which constitute almost 80% of the industrial applications. We're mainly concentrating on this type of pumps. Peripheral pump, I've already told you, it's basically at the bottom right, you see this picture that you pump is sucked on the periphery, and then the like turbine blades, they move, and this, because it's concentric, it gets pushed, and it is pushed out of the chamber here. This kind of pump are also known as turbine pump or regenerative pumps, and they have high discharge head and very low flow basically. Then you have axial, mixed, and radial pumps. Let's just have a look at that, how they look like. The axial pumps are, simply like axial flow. You have vanes which is pushing the liquid the backward on a single shaft, and you have very high flow and very low pressure. That is the one characteristics mainly on the irrigation or lift irrigation. You have those kind of pumps, and you have even in the salt works, you will find a lot of these kind of pumps, which you don't need much of head, but you need a lot of volume. The whole seawater is pumped into the salt forms. You have a mixed flow, which is a combination of radial and axial, and you have radial flow pumps, which is like, typically which has very high pressure, and of course the pressure flow relatives are lower. There's on the top also, you see this, the radial pump, which we talked about. It is a mixed of both, and the axial is of course in the axial direction. You have now, where are the applications for this? You have a comparative chart here: centrifugal pump, reciprocating pump, and rotary pumps, which is also like peripheral pumps. The optimum flow and pressure application, medium to high capacities, is the low capacity, and this is a low to medium capacities. Minimum typical, this is in gallons per minute. So 1 lakh gallons per minute, 10,000 gallons per minute. And you have maximum pressure. Of course, the pressure highest is developed by the reciprocating pump, as you all know. Does it require relief valve? No, it does not need. In centrifugal pump, you can have it when shut off. It can continue to rotate till the liquid gets heated up. But here, no, it will burst the basically pipeline also because it's reciprocating. And then you have a variable and constant flow. Yes, it's a variable flow here, but it's constant. One piston stroke actually is the one flow. So that is fixed. You cannot change that stroke length. Yes, you can change the RPM, of course, through VFDs and all that. But otherwise, by nature, unlike a centrifugal pump, it is not a variable flow. Then they are self-priming. Centrifugal is no. Yes, they are self-priming because they are pushing the liquid forward and backward. The space constraints, they requires less space, and it requires more space in the reciprocating comparatively. The cost wise, yes, it's a low cost. Yeah, of course, very costly affairs. That's why you find that it's getting phased out in most of the application. Unless it is a very viscous and thick fluid, people normally go for centrifugal pump, and all kinds of fluid that are being handled here. Now, typically, if you see what is the energy that you input to the pump. Now, if you input to motor 100 energy, now motor efficiency, let's consider as 90%. So what is motor output? You're getting only 90% of the 100 units that you got. Then there are transmission losses, belt, gears, etc. You get about 5% loss. So you get further 5% reduction in useful energy to the pump is only about 85.5%. Again, there are coupling losses, the footfall losses, friction losses, etc. About 5% if you knock off, then you get about 81 as a at the pump, and then pump efficiency is 70%. So you get equivalent hydraulic energy is only 56%. Then there are losses in the discharge pipe and the pipe fittings, etc. Let's say if you consider it is about 10%, then you get a efficiency or actual output. At that point, what was 100 input to the motor, we are now ended up with 51.2%. And if you consider that, yes, normally you always have a margin of 10% on flow pressures, etc. So you end up basically what was useful as 100 units of energy, you're getting only 46% as the output in terms of the hydraulic power. In terms of the life cycle cost, if you see, the initial cost is about 5%. 5% is the maintenance cost. The major chunk of the life cycle cost is the energy cost. So its energy is very, very important for this kind of things. Now let's concentrate on the centrifugal pump. Centrifugal pump looks typically like this. You have a suction nozzle, which is the eye of the pump, as it is also called. Then you have a rotating shaft where you have two bearings, which is driven by the motor here. Then you have an impeller. Now that's mounted on the pump shaft, and the pump, due to the centrifugal action, gets out into the discharge. And then you have various other components like casings, and you have a seal here, you have a shaft and oil rings, etc. This is how it typically looks like. Now let's come to the pump selection. How do we do a pump selection? The first requirement is that we have to find what is our requirement. What do we need? How much is flow? What is the pressure we need? Because that's a design aspect. Normally, you have a process diagram, and from there you try to arrive at what is the flow, some typical heat exchangers or some columns, etc. So you will get to know what will be the head requirement, what will be the flow requirement. As is through a process and energy balance, you do heat and mass balance to work out what is the cooling water requirement, and so basically you can arrive at the design aspects of it. And then the layout of the typical building, like you may need a sort of a barometric lag, if you have a vacuum system, so you need at least 36 feet of lag. So you have to send the the water to that particular height. So once you have arrived at the design figures, there are top 5 things to know properly to size a pump. One is a differential pressure. What is the differential pressure from suction to discharge that it has to develop? What is the fluid temperatures in degrees centigrades? What is the viscosity? You may have centipoise or you may have Pascal seconds. Flow rate, what is the meter cube per hour? What is the density? And what is the corrosion properties, to decide on the MOC, metal construction of the wetted parts of the pump, basically. So once you know these parameters, Then you arrive at a total dynamic head. Now, dynamic head is basically summation of the static head, then static lift, and the friction head. So static lift is basically, you have a negative suction. You let's say sucking out something from the well, basically. So it has to suck out. So that is the lift. What is the lift till the eye of the pump? That is a static lift. And the static height is the maximum height reached by the pipe on the discharge side of the pump. So that is the static height. That is what is the elevation it has to discharge. And HF is the friction factor in all the pumps and pipe fittings, etc. Pipes and pipe fittings that you have, bands and reducers or any flanges or even valves or control valves, etc. You'll have a lot of losses happening. So all this theory put together give you a total dynamic head. So you have to find out this. Then find the specific speed. Now that is a very, very important parameter, often not taken care of during the design stage, but it is at the design stage that you can make use of this. Now, what is this specific speed? It dictates the pump geometry, impeller type, and the HQ curve, that is head versus flow curve. Now, very, very important parameter. We'll delve a little more into this in the subsequent slides. Pump family curves, we have to find out. We get the frame sizes, required head and flow for a given RPM. Now, what is the RPM of the pump? Normally, it depend on the what poles of motor that you're using, directly coupling with the pump. Of course, if it is a different RPM that you need, then of course you'll have to have either gear arrangement or a pulley arrangement. But these are all leading to losses. The preferred thing is you have a direct coupling or a direct connection to the motor. So motor will go either if it is a 3000 RPM, because 6000 is the 120 F by P. If you take that 2-pole motor is 3000, then 4-pole is 1500, then you have 1750. Like that, you will have to arrive at what is. So it's always preferred to have a lower RPM because it leads to lower wear and tear and lower maintenance. So lower the RPM, better it is. But then if you have very low RPM, you will not be able to develop a proper head through a centrifugal pump, etc. So we'll have to, sort of a trade-off to find what is the actual RPM required. Then you have to know the pump characteristic curves, which gives you a head efficiency, power, NPSH, net positive section head. We'll dwell in detail about it, and the flow of the water. And then the pump certified curve. What is the pump certified curve? You normally at the design stage, you ask for pump certified curves. I need. Now, pump certified curves are curves which are given for a particular pump on the test bench by a manufacturer. And it is only default is water, because he is going to use only water, but your application may be some solvents or something else. Now you will have to do the corrections. And again, what are the corrections required and curves, etc. We'll share some details in the subsequent slides. Now, what is specific speed? The specific speed formula is N under root Q. Q is the flow rate, liters per second. G is the gravitational acceleration, and H is the head. It is in meters. So N under root Q GH 3/4. This is what is the specific speed. Once you know the Q and you know the H, the first thing you can find out at the design stage is what is the specific speed. And once you know it is in terms of the numeric, it is just 0.5 and 0.75. So it's just the numeric conversion of this. So nothing to worry on that. Now, once you know the specific speed, as a thumb rule, if the specific is approximately 25, then radial high-speed head impellers are preferred. Up to 40 radial medium high head impellers are preferred. Approximately 70 radial low head impellers are there. At 160, this is the specific speed. Specific speed means it is so if it is about 160, it is mixed flow impeller, and if it is 140 to 400, then you have to go for a axial flow impeller or propeller type, basically. So this is how it is moving. If you see the kind of, this is basically a radial, very steep radial, then gradually it is moving towards the horizontal axis. It comes to a mixed flow where it's a radial plus axial, and then you have absolute axial. So depending on what is your specific speed is actually a dimensional dimensionless entity, which you have to find out the design stage, then you know what is the kind of curve where you're fitting in, and accordingly you ask the supplier or manufacturer that, yeah, I need Excel propeller type, or I need a mixed kind of flow. They'll give you a basic guidelines on that. Once you have done that, of course, this is another way of showing you the same. This is the specific speed. Now this is 500 to 15,000 is the specific speed. The x-axis it is given. Now this is the efficiency in percentage, and this is the flow. What is given here. So you see at this 10,000 GPM, this gives you a good amount of efficiencies, almost about 90% you can reach in this specific speed range. And this is actually the corresponding curves. So from mixed flow to the this axial flow here, radial to axial. Now this is how the curve moves from vertical to going gradually to horizontal, and then in axial it is absolutely horizontal flow. Now, if you see the curves, again, on this side, radial, you will have, these are the typical efficiency curve. You see the head curves are getting flattened out. Efficiency curves are moving slightly on the, so as you move forward, the efficiency is at a very high capacity compared to the, the radial efficiency. At this point, radial is maximum, but at this point, this mixed may not be, the mix will be slightly here. And if you talk of the axial, the efficiency will be highest, maybe at the very, very high flow. Head may not be that high in requirements. There's another curves, how specific speed, most often not very popular dimension or entity to looked into, because operating and maintenance staff already have an entity in their place. But I'm talking of how to select at the design stage. That's where you have to have this parameter, which is very important. Now here it is giving you specific speeds are here. So red is the highest, that is the axial flow, and 600 ns. This is almost flat. You see, this is a break head, percentage of head and percentage of flow. You will find as you go radial, it is almost flat kind of a curve. Whereas in terms of axial flow, the head falls very steeply. So this gives you a much better control for flow, because it's falling up very. Whereas here it will be almost same constant head. You are going to get it here. This is, of course, a variable speed curve for pump with specification of 1654. So the speed is already given, and then you have these different curves. This is the system curve, and all these are design curves basically, and these are all efficiency which are tabulated here. This is again gallons per minute versus head flow. So basically, you will find that pump efficiencies are somewhere here, and subsequently we'll come across to know how the efficiencies are decided. Then you have impeller. Now you have three types of impellers, basically open impellers. They give you very high flow but very low head, and fluids and slurries, low efficiency but easy to make and maintain. So this is very cheap actually. We would still give you, but this is open impeller. This is semi open impeller, or again you have for wastewater those comparatively higher efficiency and high head and low flow. And then you have this is for the closed impeller. A semi impeller is somewhere in between. The closed impeller gives you you can have wastewaters or higher, much higher efficiency in the closed impellers. Your high head and low flow, and can be used for clear liquid, solids, and generally used in the process industry. You will find most of the process industries using this. Then, of course, when you have impellers, you have forward curve, backward curve, and radial. And you will see if you see the head, this is actually the backward curve. So this is the pressure versus the flow for the backward curve. This is for the radial curve, and you will see this is for the forward. Now forward, the efficiencies are comparatively very poor compared to the backward. It has the highest efficiency. Now let's come to the family of selection chart. Once you have arrived at a specific speed, you know the flow, you know the pressure. You have to tell the manufacturer that, okay, please give me the curves. Let's say you had and you have preferred a low speed curve, basically. This is the 1750 speed curve that has been given by the manufacturer. Of course, this is all US slides, so that's why you're seeing 1750 or 1800 as the curve, because it's 60 hertz is their frequency. So let's say you have you needed US GPM as 10,000, and you have a requirement about 80 as at 80 feet as the head. Then you find here is that you are falling within 46-10. Now, what is this 46-10? But of course, you will also be close to, if you remove this curve, you will also find that even 4-13 also is equally close to this. So there are two actually primary selections, 4-6-13, 4-6-10. Now, what does this 4 and 6 means? 4 is actually the discharge diameter of the flange of the pump, and 6 is the suction. Suction is always bigger because you need less friction losses. We'll come to it when we talk about the NPSH. Always you will find the suction pipe is larger, suction flange in the pump is larger than the discharge flange. And 13 or this 10 is actually the diameter of the impeller, which is the largest diameter of the impeller in this particular range. So always try to select as low pump speed as possible so that your maintenance is reduced. Now, what are the pump performance curves? Pump performance curves are basically HQ curves with which also gives you efficiency. Now, these are all the curves for different diameters. Now, this is 9.5 inch diameter. This is 9 inch diameter, 8.5 inch diameter, 8 inch diameter, and 7.5 inch diameter. And these are the parallel lines. So as you move up, the diameter increases. Now, these lines, which are slightly curved lines, they are basically efficiency curves. And you see this efficiency curve moves like this, and it's a full like a semicircle. So from here, anything on these points will be at 73. Anything on this point will be at 74. So this is 74, this is 74. If your point is here, your efficiency is 74. If you select a pump, this particular here, then it will be 72 as efficiency. So obviously you want to have the maximum efficiency. Now these are the efficiency points as this half bend lines that you're seeing. Of course, it's actually if you take the curve, will go, all efficiency curves will go like that. Then you have on the top actually is NPSH required. It is R, NPSH R. Again, we'll come to it. What is R and what is A, and what is 0.3 or 3%. These are all different nomenclatures. We'll understand it as we go further. But see, this is a typical NPSH curve. You would find that as the flow increases, NPSH also increases. So keep that in mind. And these are all known as performance curves for the pumps, basically. So the largest in this particular pump, largest impeller that you can accommodate is 9.5. And the minimum size that you can accommodate in this particular pump is 7.5. So within this range, you can operate, and wherever you have, always try to select somewhere in between, so that in case you need to have little higher heads and higher flows, then you can go impeller up and you go impeller down. Try to select a higher ones as possible because that gives you flexibility. So because higher ones can be trimmed, you can even turn the diameter, reduce it even in your workshop, and maybe reduce it to half inches, so it comes to 9.5 can be made into 9. So that is possible, but always try to see that. And you will see as the flow increases, the head goes down. So head is actually inversely proportional. This is a very typical characteristic of the centrifugal pumps, which is 80% to 90% population in any industry you will find of the centrifugal pumps. That's why we are talking mainly of the centrifugal pumps. So impeller dia selection, let's say if you have 9.5 and this is the 9 inches, but your curve, your application is somewhere here, let's say, for example. So how do you calculate that? Very simple. It's interpolation. But yeah, I mean, this is just a formula for interpolation. This side is the delta H, and this side is the delta. This side is the diameter of the impeller, basically. So 9 is the minimum, plus you have to add 9.5 minus 9 divided by what is the head difference that is compared into the operating head minus h at 9. So from here, so you will come somewhere around here, and you will get what is going to be the diameter of the impeller that you would need. Again, on impeller diameter, you would find from these curves, if there is an existing pump, of course, you already know, but in a new pump, you have to examine several pump performance curves and select according to the pump curves. At zero flow, that is this point A, it's a shut-off head. That's the maximum head that the pump can develop is here. Of course, you can turn it, but water will be churning, and then at one point of time with the heat, will convert into steam, and then there'll be a lot of leakages and problem in the pump, of course. Then, and the point B, now this point B is the runout point. Runout point is beyond this, the pump will be unstable in operation. There may be cavitations and issues of this nature. So it is never desired to select a pump somewhere, or your curve which should come somewhere, system curve should not come very close to B and very close to A. So select pumps accordingly. Then best efficiency points is the best efficiency point of the pump, which is actually, let's say, 74. Now, if you see at 74, this is the horsepower. This slant lines which are cutting are giving you the horsepowers actually. So if you see the slant lines, this is 3 horsepower. So all pumps, all application which are having this between 2 and 3 can be handled by this 3 HP motor. All application at the left of this can be handled by 2 HP motor. And all application like this particular point, if you are operating, then you need a 5 HP motor here, because it is on the right of the 3 HP curve. So once you do the impeller size selection, select the impeller that can be increased or reduced depending on the actual situation in the plant. Select and pump operating point 80 to 100% from BEP. So you see this 80 to 110, around that is okay. I mean, when you're selecting application, because there will not be much of a difference, because this curve goes like this. So any point here to here is all 74. From here to here, it's all are 73. So from this point to this point, all will be 73. So not much of change will happen. So you choose which has 80 to 110 degree, and the percentage, sorry. One can always change impeller one size up or down and trim to the desired size. We already discussed that, and trimming more than 10% is not advisable. Why? Because then the gaps might increase, the performance curve might change, and then a lot of backflow might start, or the pump characteristic curve itself may change. So it is not advisable to do more than 10% in pump trimming. Now, what is certified curve? As I told you, when you ask the manufacturer to give you a certified curve, he'll give you for that specific pump which is put on their test rig, and then they plot the curve. They continue, increasing the flow, and they continue, sort of throttling the valve so that head increases and the flow changes. Accordingly, they'll keep plotting the point and give you a curve. Now, this curve is actually and the power requirement. So power, flow, and head, they'll give you. NPSH, how it is calculated, I'll tell you a little. Wait for a while till we come to NPSH. But then this is how the certified curves. These are curves which are only for water, because he'll use it only for water. Fluids having different viscosity than water. Apply correction factors for the head flow efficiency, published by Hydraulic Institute, HI. You can go to this website, http://www.pumps.org, and the correlation factor chart is fluiddesign.com. These are two things where you have to apply correction factor to the certified pump if your fluid is different than pump, because he will give you only certified pumps for water application. Now let's come to what is NPSH required. There are two types. In US, they follow this system where on the top of the pump curve, they have this NPSH requirement, and other, like SI systems, you will normally have the pump which are having NPSH on this side. So most of you will be familiar with this NPSH at the bottom, this line, NPSH. required. So pump, whatever is given in the pump is the required, whatever is required actually, not what is available. So these are two things which I wanted to just share with you. Now, what is NPSH? Basically, there are 3 or 4 terminologies. But before you understand NPSH, let us first understand that each fluid, each liquid has a vapor pressure. And this vapor pressure, if you see this chart here, all liquids follow this particular characteristic, that as the temperature increases, vapor pressure also increases. So is the case when the pressure reduces, the vaporization point. So the vapors, the liquid will boil much faster at if you go to Himalayas, then when you are at Chennai, because of the atmospheric pressure has also increased, that much height of the atmosphere has also increased. So the boiling point will be higher in Chennai, lower in. So same pump was running okay, but when you shift to, let's say you have a plant which was in Chennai, now you're shifting that plant to, because of some concessions that government has given, to maybe Himachal Pradesh. And then you find that this pump has started suddenly cavitating, or there's a lot of vibration noise which is happening, is not pumping properly. Everything was okay when it was in Chennai, but not here. So you have to take care of this. That's why you must understand this one particular characteristic which is very, very important: vapor pressure, not only of water, but any fluid that you are pumping. Now, you are all aware of the simple energy balance equation, which is the Bernoulli equation. That is pressure head, velocity head, then static head, and whatever is the friction head. So basically what you do is you do a Bernoulli at this point, which is the source from where the water is coming, and at the pump suction. So this is, if let's say if it is a 0.2, then you will do a Bernoulli. Here velocity is 0, here velocity will be some velocity v2, and there is a static head here, HS, which is the lift, actually static lift, which is happening, and then there will be some suction losses, HF, in the fluid, depending on the pipe, etc. We'll come to that also subsequently in the slides. And then there's a band also which will also incur some losses. So basically, when you have this kind of a configuration, let us first understand what is NPSH available. A is available from the given configuration. So this is nothing but, let's say if it is open to atmosphere, it is P by rho g. If it is a pressurized closed vessel, then you will have to put that pressure here. And P by rho g means that is all, everything is converted into head terms in meters. V square by 2g is V is the velocity here at this particular point. P is atmospheric pressure. And then you have PV is the vapor pressure of the liquid. This has to be more than 0. If it is not more than 0, then the liquid will vaporize. Or maybe this equation at this particular point, that is at 0.2. 0.2, it has to be more than, pressure at 0.2 is more than the vapor pressure of the liquid. In another terms, if you see, NPSH-A is suction head minus the vapor pressure. That is the suction head. This is what we are saying. P2 by rho g, V square by 2g is the suction head, and vapor pressure is PV by rho g. So this has to be more than this, then only cavitation will not happen, or vaporization of the liquid will not happen. Otherwise, the pump will take air, and or pump will take vapor and not pump anything. Then so NPSH available is actually HA is the atmospheric, then static lift, then you have friction losses, and minus the vapor is what is available. This is what. So hope this is clear. NPSH R or R is net positive suction head required. Now this is what is given by the manufacturer. This is what is available with you in this given configuration that your designer has set. That okay, I will keep my pump here, tank will be at the ground floor, and something like that. Now, what is NPSH? Again, terminology is, there's one more terminology, which is NPSH 3 or 3%. You will come across this point also, which is given by the manufacturer. Now, this is a property quoted by the pump manufacturer, the suction pressure at which the cavitation has already reduced pump performance by 3%. Now, how it is done is actually they will keep the test rig. You see, the manufacturer will put the pump in the test rig and keep the discharge valve fully open, so the flow is constant. Now at the suction valve, he'll start throttling. So once he throttles, what will happen is, of course, there's a increased pressure is getting reduced here at the eye of the pump. So the moment it gets reduced, and if the discharge pressure falls by 3%, this is what it is saying, the NPSH AN head required. So if you have wherever the head falls by 3%, that is the point at which, yes, some vapors have started forming, but it's not the point of cavitation. So this is the point which is called as NPSH 3 or NPSH required. Below this, cavitation is bound to happen. So that is where they use this terminology, NPSH 3 or NPSH 3%, if you come across. Then some people also have of course, NPSH-A we have already discussed. Then NPSH 40,000 also is sometimes a nomenclature which is used. This is actually a guaranteed for no damage, because if the cavitation does not happen, there is no damage to the impeller or the pump casing which is going to happen. So the manufacturer gives you NPSH 40,000 is what? That is 8,000 hours into 5 years guarantee it is giving you. That is standing guarantee that this pump, if it is operated above this required NPSH R, will stand NPSH 40,000. Now, there's another terminology called NPSH margin or ratios. Now, what is NPSH margin? Is NPSH available minus NPSH 3 or what required? What is, both are same. So NPSH ratio is NPSH available divided by NPSH required. Now, reference NC, this is Hydraulic Institute, 14.6 rotodynamic pumps, hydraulic performance acceptance test. They give you a table. What does the table say? For the boiler feed water pump, if the power requirement is less than 225 kilowatt, the smaller pumps, then preferred operating region, this is PORH, preferred operating region is 1.1. This ratio should be 1.1. And if it is AOR, it is allowable, is 1.3. Okay, so these are all guidelines at the design stage when you're doing a selection and when you're doing your physical layout of the pump and the tank and the system where it is going to pump should be. So this is another NPSH ratio also is equally important to keep it in mind. And POR is preferred operating region, and as per API 610 also mentions this. Now, what is cavitation actually? Now, we have come to NPSH. So why NPSH? Because NPSH is not there, available is not even as required. Then what will happen? Let us see this. See, this pump has, it has started sucking. So pressure will keep on falling slightly. There is a slight fall because of friction. From here, the pressure was up. Now it is falling slightly. And then at this point, it is falling here. Because there is a direction change. So there is a lot of loss happening at the eye of the impeller. And then it is discharging. So at this particular point, there is a fall in pressure. Now this fall should be above the vapor pressure. Let's say this is the vapor pressure line. For example, this is the vapor pressure line. So if it is like this, it's good enough. There will be no problem. But supposing at this point, if the cavitation, the vapor pressure falls below the vapor pressure lines, this particular drop falls below the vapor pressure line, then the bubble formation will take place and you will definitely have a cavitation. So your NPSH is available and this is what is required. This is the margin which is there, and it should be followed as per the norms which are given here. Again, NPSH chain required, very, very important, because many times I have come across, even during audit time, people do not understand this and they keep on putting a higher flow pump, higher capacity pump, that no, it is not pumping. If you put higher capacity pump, more cavitation will happen, because the NPSH requirement, if you see this, as the flow increases, NPSH requirement also increases. So the requirement also will go up, but your frictions you not change anything, increase the flow, though cavitation will start automatically. So that's not a solution. So you see a typical case. You have a positive head. There is a myth also, that if the tank is on the top and pump is at the bottom, and cavitation will never happen. No, it can still happen. How? You have a positive head and you have a fluid pressure actually, which is zero pressure. It's absolute here. Now, this is the pipe friction and this is the vapor pressure. So available is this much, and the required is up to this much. So there is still a gap. Available is more than what is required. This is NPSH available and this is HPSH required. So this is okay. But for example, if your pipe friction is much higher, supposing you have a wall or some construction or there is a branching which is going from the suction side, what will happen is the friction has increased. The fluid vapor pressure is same as this, but the friction head has increased. So your absolute available head from the 0 point is only this much, whereas NPSH R was here. So this will definitely have a cavitation. Now, how can NPSH A be changed? Because available is what is your the pump is R. A is your baby, basically available. So your baby, by changing configuration. How can we do this? NPSH A can be increased by lower the pump suction below the suction tank. So what happens is you have a tank at 0, but you dig a pit and put the pump inside the pit. So now you have a positive head. So you have increased the head in the pump. So suction head is increased. Or you relocate the suction tank at a higher elevation. Or if you cannot go into the pump into the pit, then you raise the tank height to the elevation from where the pump is sucking. Or keep a higher diameter suction pipe to reduce the friction losses. The friction losses is reduced by d to power 5. So keep that in mind. Maybe have little more liberal piping. And keep the fluid temperature lower to reduce the vapor pressure. Okay, there's another idea is that you cannot do anything. It's a fait accompli for you. Then okay, if you can maybe reduce the vapor pressure by lowering the temperature, because this vapor pressure, as the temperature goes down, vapor pressure also goes down. Okay. So with this, we have understood what is NPSH A, NPSH R, NPSH 3, NPSH 40,000, NPSH 3%, and what is the implication. Now let's say how the cavitation happens. Now you see, I have the impeller. You have suction coming in, and then this will have a change in the direction. A lot of losses will be happening in the impeller, and then it will changing direction, etc., going there. Now what happens is, supposing your bubble forms, which I have, these are all pictures of cavitation implications. This is the whole metal. How much hard metal also has gone away. What happens is when the cavitation happens, there is a bubble which will come here. Now this bubble actually will come under the pressure as the bubble moves. Now as it moves away, so it is going out. So it will be subjected to pressure. So from the top side, it will start sucking in. Sulking in actually, and then at one point of time, this will burst as a microjet, because the bubble can't remain as a bubble. As it goes forward, the velocity reduces. Say here velocity is highest. As the velocity reduces, pressure increases. It's Bernoulli, typical Bernoulli. So as the pressure reduces, as the velocity reduces, the pressure increases, and this is how the formation takes place. And you have like a arrow shooting, bullet, like a bullet. It will hit here the surface of the metal, and some particles will be eaten up, and then they'll be carried forward along with this. So this is a typical cavitation phenomena which happens. Now this will even change the characteristic of the pump, which was originally there. You don't know, pump is running. I've seen a horrible condition that almost the all impeller, this thing is eaten up. Pump is running. So what happens is they say, okay, cooling tower, okay, one more pump you run. So they run two pumps. It is eating up energy, not pumping anything. And that is the situation which happens. Now, pump head calculations, the head required to overcome the footfall losses, suction lift, suction pipe losses, suction band losses, discharge band losses, discharge pipe losses, pipe fitting losses, and of course, discharge static heads. All this have to be overcome by the pump. So let's take one by one. The footwalls, actually, wherever you have a footwall required, if it's a negative section, normally you'll have a footwall. Now, footwall also different. I've just taken a typical example. So when you see the footwall, it'll give you different sizes here, and also it'll give you a curve. All manufacturers are bound to give you a curve. If they don't, please ask them. This is a flow, and this is the head loss. So you know exactly what is the head loss. So you know whether you have put a sort of a footwall which is having so high a loss that the cavitation is started and it's not really lifting up. So you have to keep that in mind. This is another type of footwall, and you see the curves are here. It is a flow versus the head loss for different sizes of this is different size. So you have to select a particular size of the pipe, let's say, because you already taken section size is normally a liberal size, which is higher, and you take that, let's say it's a 4 inches, the 4 inches will be somewhere here, and then you at that particular flow, what will be the head loss is you have to read and take it up. So this is the footwall losses you have to calculate like that. Friction factor and head losses in the pipe. Now we are all aware of the Reynolds numbers. Is a very important dimensionless entity, which is rho v d upon mu. Here the fluid dynamic viscosity is mu, is meter seconds. Rho is the kg per meter cube density. Its velocity is meter per second, and pipe diameter in meters is d. So you calculate a Reynolds number. From the Reynolds number, if it is a again, if it is a laminar flow, that is less than 3000 numbers, you can use this as a friction factor for laminar flow. And if it is a more turbulent flow, then Colebrook-White equations to find out what is the F, friction factor. This is a typical equation for the friction factor, but it's a little complicated mathematics that we have to do. So better to go in for another method. Let's Moore's chart. Or first you come at a Darcy-Weibach formula. What is done here, Darcy-Weibach formula is this is the head loss, this is the friction factor F, which we can find either through this equation or from the chart, which is much easily available. Nomogram is available. L by D. Now L is the equivalent length. It is not just the length of the pipe, but equivalent length, because there will be band, there will be sort of flanges and some reducers and expander and small radius or large radius bands, etc. will all have different velocity is known, G is known. So it will be easier to calculate what is the head loss. Now for F and L, let's find what is the equivalent length first. All pipe fittings, you see your regular 90 degree, long radius, regular 45 degree, line flow, branch flow. So for depending on the pipe size, you have this equivalent length in meters. So what you have to do is, let's say your suction pipe is 10 meter. You have to then find, okay, my regular 180 degree return band is available. Then its size is, let's say 4 inches. So you will have 4 meter of equivalent length you have to add. So 10 meter plus 4 meter. So now equivalent length when you take in this formula will be 10 plus 4. It's not only the pipe length, it is the equivalent pipe length. All these entities which are there, elbow, tees, returns, walls, strainers, etc., they are all sort of given some particular values which have to be added and to arrive at the factor. And for the friction factor F, which was in this formula here, we have to find what is the F value. Now this F is from the Moody's chart. Moody's chart is actually a Reynolds number. We already know this. We have to know the relative roughness factor, which is epsilon by D. Now epsilon is actually for different material. These values are already defined here, that is concrete or is pipe or is steel or rusted steel or forged steel, or so basically, or main pipes, etc. So epsilon is known. D is the diameter actually of the pipe, which is known. So you arrive at this roughness factor. So you know the roughness, you know the Reynolds number, and the third is you know the this is the Reynolds complete turbulence. You know the roughness factor and this, so you will arrive at this particular friction factor here. Now let's come to we know all the head requirement, we know the flow requirement already through heat mass balance and the process extra, that what we need. So we have arrived at what is the hydraulic power now. Hydraulic power is QH rho G divided by 1000 NP, and what is NP is this is the hydraulic power. So for pump power, you divide this hydraulic power by the pump efficiency, and what is the motor input is this pump power, you divide it by the motor efficiency. So you arrive at the motor input power. So this is how a very simple formula that you can do. And as we have said in all the curves here, for a particular 8.5 diameter impeller curve is here, pump performance curve, and this is the HP lines. So 3 HP to 2 HP is all 3 HP, 5 HP to 3 HP is all 5 HP. Higher one you have to take and arrive at this. Now, pumping system dynamics. Because in pumping system, actually in any industry, it will be very dynamic in nature, because there will be reservoir level will be fluctuating, your process requirement will be fluctuating, there will be changes in valve setting, control valve will be, maybe it is based on the temperature or levels or whatever is required. So this is a very dynamic system which is happening. Change in the pump, inlet and casing, because even impeller, supposing some time cavitation has happened in the night shift, and then the impeller has got damaged. So again, the curves will also change. They will undergo, they will not be this smooth. They're not a doubling head. Maybe it has come down somewhere here. And changes in the system curve due to scaling and heat exchangers, etc. The system curve is like this. Now, you know that this is my pump performance curve. This is my system curve. System, this is the elevation. I have to, let's say, send it to the top floor. So this is the static height that I have to raise this water. And then as the flow increases, there will be friction losses. So head requirement will go like this. So this is the, and as you keep closing the valve, the the pump system curves will go on bending it till the time it goes vertical here when you have totally shut off the valve. This will be the point at when you have shut off the discharge valve and pump is still running. So the pump goes like this, all valves are open. So this is the point at which it cuts. This is the operating point. This is where it will operate. There is no choice. It has to operate at this particular point. Now you want less flow, then you close the valve. The pump curves come here. But then, you know, in the efficiency were like this. So because of closing valve, the efficiency now is a different efficiency, which is having at point B. So, so we have to keep that in mind. Excuse me. Now, we have a choice. Let's say we can have multiple pumps. You know, in multiple pumps, there are two choices. You can have it in series or you can have it in parallel. The pumps in series, what happens is the head will increase. So this head, because flow will remain same. Whatever is being sucked here is pumped here, it's sucked here, it's pumped here. So the Q is same. For every Q, you will have head which is not double the head. What was in pump this, the head will go almost double here. Whereas when you have parallel pump is heads are same. But because of the flow has increased, so the system curves will go like this. Sorry, the equivalent curve of the pump, equivalent pump will be like this. Now you see the what happens is as you increase the flow, the friction factor also increases because Reynolds number is increasing now. So friction factor will keep on increasing, and that will result in more head losses. So sometimes you will find that it is when you have pumps in parallel, the flow should be like up to here. Then you put another pump, it should go somewhere here. But actually, the system curve will go like this because the friction factors have increased. Sorry. So, so in the pump characteristic curve, let's just summarize before we move further. At the shut-off point, there is no flow. The power consumption is 30 to 40% in the pump. You see the power curves, brake horsepower. This is the HP. Okay, this is the shut-off power. See, almost 30 to 40%. Okay, this is the horsepower. This is the water horsepower, hydraulic, but this is the pump horsepower because pump will need something to come over the inertia. So it will start only at when 30% of the power input has taken place. And you know, this is the efficiency curve. This is the pump characteristic curve. So the motor load at no load is 5% of the full load. The pump is about 30%, But you see the motor, when you just run the motor idle, it may be around 5 to 10% is what it will draw. But pump will draw 30 to 40% because it needs then system configuration. Actual flow in pumping system will be determined by the pump system characteristic of HQ and system configuration. System configuration is actually the static head needed, P and ID, what are the valves, etc. Then what is the MOC, because the friction factor will depend on MOC. What is the size of the pipe? What are the pipe fittings? What are the bands, branching, reducers, expanders, etc. that you put? What are the valves, that is foot valve, isolation valve, control valve that you... So system configuration decides the system head, which again, depending on the flow, we know each manufacturer will give you at this particular flow and this particular valve position, what is the delta P, the pressure drop across the... So accordingly, you can draw your system curve. Typical pump efficiencies, normals are 60 to 75% is normal, but you can really maintaining very well all pump, motor, couplings and lubrications and vibrations, everything is fine. 70 to 8 to 85, up to 85% is possible. And the worst is, this is what normally you will find in old plant which are not very careful about the pumps. You will find efficiencies only in the range of 20 to 50%. Now, pump capacity control. Yes, you can have on-off, recirculation, valve control, pump speed control through reduction pulleys. Mechanical system, you'll have variable fluid couplings or variable gearboxes. Electrical, you'll have eddy current drives, variable frequency drives, 2-speed motors. Pump modification itself, you can do, change to a lower impeller or correct the pump size, etc. So these are all points through which mechanical, electrical, and pump design modifications that you can do. This is the actually a typical throttling loss that we have shown here. This is a pump characteristic curve. Now you see, you wanted only present. This is what was the present PQ LPM that you wanted, and the head was around 23.2 meters is what was your requirement. But now you need less flow. Let's say you need only 9,000 flow. So you have throttled the valve, but by throttling you have increased the static pressure also. So it has come somewhere around here, and this will result in losses. This is the amount of loss which has happened actually, because you could have, supposing you were here in this line, then you needed only the flow, 9,000 flow. This could also come by if you were having a lower diameter of the pump, or maybe a lower speed of the pump. Then also you can reduce that. That will give you this much amount of saving. This is a typical where you have throttling versus the variable frequency drive, you see. So from 12,000, 9,000, you see the pressure will reduce when your pressure will increase when you're throttling, because the back pressure of the valve has come now onto the pump. And if you further reduce, so these are two actually, this is the throttling and this is the VFD. If you do VFD, the head requirement will be only because it falls in the square of the, as per the affinity law. We'll come to that subsequently. Okay, so the pump efficiencies, you see, which was 86% has come down to 79 when you are throttling the valve. In VFD, it is almost close, 85% only, because you have shifted the curve below. And pump kilowatts, etc., and the saving will be shown here. Now, what is the affinity law? All in the centrifugal machines, all centrifugal machines, whether pumps or fans or blowers, you will have capacity is proportional to RPM, head is proportional to RPM square, and power is proportional to RPM cube. If the RPM is reduced by 10%, the changes occur as below. Capacity is reduced by 10% because RPM is directly proportional. Head will be reduced by 19%, and power will be reduced by 27%. In reality, due to losses in VFD, the actual savings are not cubic, but this is practically we have seen, and it has been demonstrated in many places that it is not the cubic saving that you will get, especially when you do energy audits, etc. You should take very conservative saving at about 2.67%. But there are limitations in affinity law. What is the limitation? It is applicable to only centrifugal machines. Like if you have reciprocating machine, this is not applicable. Reciprocating, maybe it is just proportional to the power. It is not a cubic proportion. Not applicable to constant torque applications like conveyors, or where you have a very viscous fluid where you need high torque, or where you have very high static pressures. It may not be really available. Is applicable only to equi-energy system curves like A. Now you see the A, when you if it is going down, it is like you see the curve 72 to 73%. This curve is actually up to here is all 72 to 73%. There's not much change in efficiency. But if you are talking of B, you see the efficiency is falling from 72% to, if you come here, it is only 60%. In this case, you are bound to create a problem of static head, because here the head requirement is much higher compared to A. So here putting a VFD might land you up in a problem actually. So you have to be very careful where all you can use VFD and apply the affinity laws to save energy. And why pump consume excess power? Then the design is the wrong selection of the pump. Over design, normally 10% in flow and pressure is permitted as a thumb rule. 10 to 20% in power, you take higher kilowatt motor also, it's acceptable, permissible. Improper layout and pipe fittings, old inefficient pumps used, corrosion erosion in the impeller, multiple and small size pumps used, systematic engineering principles not followed, rush job, no, it's okay, ठीक है, thumb rule लगाओ चलेगा. Over tightened glands, sometimes you will also increase friction. Improper maintenance, needed clearance, impeller and the casing clearance increases, then the backflow will increase and you may not get enough heads, etc. The bearing issues, lack of lubrication damage, vibration is misalignment, loose footing, imbalances, cavitation, harmonics, all this will lead to improper coupling, V belts, etc. will also have a loss, and motor issues like bearing, etc. Now let's quickly I'll take another 10 minutes if it is permitted by the organizers. Hello.
Yes, sure. No problem.
Yeah. So okay. So now let's quickly, when you're talking about pumping a system, it consumes. So motor is one component, coupling is another component, and pump is another third component. So we have to really identify. Pump, we have seen what are all the kind of losses that are happening. But in motor, you have to proper maintenance is required. You do condition monitoring. You do through vibration analysis. You do infrared thermography. You do lubrication analysis. You have a drive system, VFDs, etc. that are taken care of. Then in the predictive maintenance, you have both corrective and preventive measures being taken care of. Motor current signature analysis is another feature which has come, because your pump is okay, couplings are okay, but motor has gone all buggered up. So what you need to do is do even motor current signature analysis. In a running, you can find out. I'll refer it to you, PDMA Corporation. This is very simple to remember. PDMA, Punjab, Delhi, Madras, Ahmedabad. You will remember this corporation. You can go there and check a lot of things, how motor health can be monitored continuously online without stoppages of anything, and then they can predict. They classify fault zones from if there is a power circuit issue, if there is a harmonic issue, if there is a stator issue, if there is a rotor issue, or if there is an air gap eccentricity issue, or if there is an insulation issue. So by capturing just the signature, it gives you which is the fault which is propagating, which is more predominant and likely, and they give you a sort of expected life which is there, so that you can take proper action. Then second is, in electrical, you can reduce voltages and run. Normally we find that there is always over voltages which are prevailing in the. Now by reducing voltage, what happens in motors? Actually, it's basically induction machine, and there are iron losses and core losses. So iron losses is I square R, which is okay, is one part of it. Depending on the load, you have to take care of that. But the no load losses in the motor, the eddy current and hysteresis losses, and these are both, if you see in the formula, are in proportion to the square of the Bmax square. There is flux density, which is actually nothing but a proportion to the voltage. So as you reduce voltage, the flux density, maximum flux density, Bmax also reduces, and your eddy current losses, which is in the square, and your hysteresis losses, which is B to power 1.6, also reduces substantially, thereby giving you some amount of savings. So let's say we always suggest that around 400 is what, if you run, that's fine. Of course, you have to, because it is done through a transformer tap changing. That is the only mechanism available to you. So when you do a transformer tap changing, make sure that the farthest point from the transformer is not hungry for higher voltages. Let's say you have a high torque requirement somewhere, because torque also is proportional to the voltage. So if there is a torque application or a conveyor application, it should be either fed through a separate route or maybe stepped up, because the rest of the motors can have impact on the eddy current hysteresis losses. And for this particular application, you can have a voltage booster or stabilizer that can be put in to improve the voltage so that it does not hamper the. So it's a you have to trade off basically and see what is the optimum value. Motor, as you say, almost constant. If you see the efficiency curves in the motor, say all the motor, especially on the higher kilowatt motor, these are all higher kilowatt motor. Efficiencies are almost close to what is the rated efficiency. Almost 90% plus will be in this range. But the lower kilowatt motors, these are the bottom ones, the lower kilowatt motor. You see their efficiency fall is very steep. Here it is almost constant, but they start falling very steep. These are motors which are up to I would suggest maybe around up to 18 kilowatt motors. It's always better if you have old motors, replace them. The paybacks will be less than a year or so. Replace them by IE3 or IE4. And now IE5 motors are also available. And to know the loading in the motor, many times your nameplates are not available. So what you do is you have the tachometer. So you just find out what is the design slip with the full load RPM. And this is no load is actually you can take even the synchronous speed. Okay, so synchronous speed minus full load, and the synchronous speed minus the measured RPM, which you can do to give you this measured by design, gives you the percentage loading. So if the motor loading is less than 50%, maybe you can even run that motor in star mode. You can reduce voltages, especially on the centrifugal machines, by that. So people do this permanently. They run it. If the loads are not there, you already taken a higher kilowatt motor. You don't want to invest in replacing with the small horsepower. Fine, you can even run the motor in star if you have all the 6 leads coming out in the terminal. Another thing is voltage imbalances. If there is voltage imbalance in the thread, especially in you have a lot of this single phase loads, etc., in the circuit, especially when you have buildings, you will have a lot of single phase loads available. So if the voltage imbalance in the motor efficiency, you see the efficiency fall. If it is 2.5%, therefore is almost 1 to 2% fall in the efficiency of the motor here, almost 2%. You see that 50% load, it's almost 2%, and efficiency falls only by voltage imbalances. From Department of Energy I have taken. And of course, now you have those replace the lower horsepower motor, all this less than 10 horsepower motor. If you replace, what is the 95 to this 85, 10% just by changing motor, you can improve. I think the paybacks are fantastic. So lower horsepower motor, please take a bulk decision. You can sell off these running motors, maybe take some money out of the salvage value and replace them to get an attractive payback period. Summaries to improve efficiencies. VFD saves power as per the affinity law, or 2.6 I have said. Weighted parts, these are all actions that I am proposing now that will improve. We can have coating of the hydrophobic non-erosive coatings in the pump, wetted parts, to improve by 5%. Sandwich flat belts against the V belts to give you 5%. Auto star delta converters. Now, wherever you have cyclic loads, you find that sometimes you need a full flow, sometimes you need half the flow because half the reactors are off, and you find the motor is running less than 50%. You can have an auto star delta converter. So if you have a star delta starter already in place, it will sense the from the CT, it will sense the current, and if it is less than 50%, it will convert it to star mode. Otherwise, automatically go to delta mode. Then pump sizing has to be proper, impeller trimming, single versus 2-stage system, optimize piping, that is MOC, like you have even CPVC is now much less frictional losses, less corrosion, etc. Sizing have actually liberal sizing even in the design stage. Review motor load and efficiency, go for more than IE3 right now. Review control system. You have now, earlier what was happening is like your machine is the ground floor and your all consumer are first, second, third floor. And what happens is invariably you will find that the first floor guy gets the maximum flow and the topmost floor guy is starving. Now the PICVs have come, that is pressure independent control valves have come. So irrespective of the pressure, because pressure will differ as you have taken out the fluid, the pressure at higher elevations will be much lower. So the flow will also reduce. And again, you will have imbalances in the system. So for that, you have either PICVs or discharge line. You should have that looping system to have the same, travel path for suction, discharge, or all flows. We'll see one of the applications here. And then pump wear maintenance, predictive and preventive maintenance to be there. Pressure exchangers. This is a new, like heat exchanger. There's a pressure exchangers have also come into foray now, introduced by some of the manufacturers. We'll share that. And pressure recovery turbines also have come in. So let's see what are these. Of course, we have seen in the when you control the flow, VFD is the most efficient part. Then you have on-off control, then you have damper control, and you have recirculation. That is no power saving. Actually, it recirculate back into the suction. We have a typical application I'll share with you in a few case studies here. So emerging technologies, we have integrated multi-stage XL pump. This is by Flowserve US. I'm not propagating, but since they are there, I'm just putting it across. Energy saving pump coatings, then energy efficient sandwich flat belts, auto start converter, energy recovery turbines, and retrofits on it. Let's take one by one. This is how the the latest pump technology which is developing. This is actually a pump and motor inbuilt into a system, and these are all in series. So there is single shaft, they are all XL flow, and each is independent module. Now it will be just pipe in pipe, just like this. There is no foundation required, nothing. You can just plug it in like a pipe in here. These are some pipe in application. Each one of these stages is independently VFD driven. The pump and motor both are together, and of course it is like a submersible pump. So motor is already cooled by this. Yeah, limitation is because the motor is also inside. You cannot have more than 90 degrees. Otherwise, you'll have to have a rational cooling arrangement, etc. But this is this is a multi-stage, propeller system that they have come up with. What happens is like you have NPSH has dropped actually, and this is now going to stop. So what you do is you VFD, this reduces, but then this will increase because it already has that additional head required, and the cavitation can be avoided. And each of these stages can be monitored in terms of the what is the GPM it is having, what is the head that it is developing, and all that. Another advantage of this kind of system is even if one pump has failed, it doesn't matter because it is all in line. So water will flow through. Maybe some pressure loss will happen here in an ideal situation, but then these two pumps will take over. Actually, the VFD will increase the speed, or so that you have the adequate head what was required and the flow what is required coming in, despite the fact that the one stage is already down. So this configuration is like the typical configuration in future will be like this. So whether you need in parallel or serial, whatever is there, this combination will be as one mounted in a setup, and then whether you need more flow, more pressure, less pressure, each stage will be combined like this, and all of them are operating through VFDs, each one of these, and they are parallel system, and then it will go to the process. So this is a new emerging technology from Flowserve. Okay. I'll come to the next stage. Is basically for coating. Pump, because of cavitation or even the corrosion, etc. happening, erosion, corrosion, a lot of this kind of stuffs happen, and then you do not get the desired efficiency in the pumps and the motor. So what is required to overcome this aging effect is to extend the life. You see that what is done is we We have done it for many systems. I'll share with you. This is the actually after sandblasting, the clean surface, and then the pump coating is done. There we check for any holidays, etc., and then the dynamic balancing is done. Because if the RPMs are much higher or kilowatt is higher, then it's always better to have a dynamic balancing of pump after the coating, so there is no imbalance happening. So it actually rebuilds this, and this coating actually is imported coating, which is hydrophobic in nature. So it expels, actually, it repels the water. So there is no addition. The friction losses are minimized, and we guarantee 5% efficiency improvement. Now, this is just one cooling tower pump we did. You will see here is cooling tower pump, 654 meter cube per hour, and 135 kilowatt it was taking. 45 was the pump efficiency. So we established a baseline first, which is jointly established, and after coating, again, you see the flow has increased tremendously. Of course, the pressure also has slightly fallen, but yes, almost same. But efficiency of the pump has improved to 75%, and thereby you're saving a lot of energy. This is another pump which was done in HCl cooling towers. Again, 55% was the efficiency. It has gone to 81%. And we guarantee minimum 5% improvement in efficiency. This is another exercise that we did. Efficiency improved to 81%. And after 6 months also, they wanted to check. And they've checked after 1 year also, actually, recently, that I do not have the figure here, and 23 also, that efficiency is almost in the same level. 2 years guarantee for the coating, etc. is also given. Then you have this flat belt, V-belt to flat belt. In actually the V-belt system, what happens is, one is the losses of wedging in, wedging out. Each of this, V-belt goes inside, and so there is a lot of friction losses here. If you take thermograph, you will find a lot of heat which is getting generated here, which never happens in the flat belt. There is no wedging in, wedging out. Second is, actually, the wedges you see here, the shape of the wedges, it's not really, it's made in castings, and there's no proper quality control because they are sold in weight, in tons actually, and bought in numbers by the buyers. So what happens is, this V-belt is having pi d n. Pi d n will be the linear speed. So this pi d n will be higher than this pi d n. So this belt will be actually running loose, dangling. You will find a lot of few belts running loose, and it's because the V groove actually is not properly there. So what happens is, all the load comes on this belt. These belts are actually resisting because the pi d n is less, d is less than this. So it is actually acts as a brake, and you end up having more energy coming in. And the third is, you see the thickness of this material, V-belts, where a set of, let's say, three of them have to be bent. And if it is let's say 1500 RPM, then almost 15 into 4 times it has to be bent and again wound around the pulleys and the wedging in action. So this, compared to a very thin flat belt system, you will find that the saving between the V-belt and flat belt, this is the efficiency gain. Again, 5% is what is guaranteed. A lot of these clients, including Reliance, Tata, etc., we have done. We've been doing it regularly here. Then auto start delta converter, I already talked about, so we'll skip that. Then, as I said, the pressure exchangers. Now, this is another technology which has come through from the same. The 90% of the flow, especially in, you talked about the RO system. See, in RO, you have a back pressure. So the reject stream is always at a very high pressure of 6 to 7 bar. And these people have developed maybe when desalination plants, especially for Gulf, etc., when you have huge desalination plants, what happens is, this is a pressure exchanger. So in the incoming stream, it exchanges pressure with the outgoing reject. So reject, actually, you don't need pressure. It has to just go to the ETP, or it has to go back to the sea. And this, whatever was the pressure, is taken up by the booster pump. So, you save on almost 98% of the hydraulic power is recovered for that. This is how, if you see it, I have a video, but I think time permits, I will do it. Otherwise, just see this. Low pressure seawater comes in here. It pushes, it comes in here. And the high pressure reject is pushing this, whatever was there. So it is rotating, actually. The rotation is also automatic because of the shape. So the concentric circles are rotating. So when this hole comes in front of here, see, this high pressure is pushing it here. When it comes here, this has already gone to the other side. where the suction part of this incoming pump will. So this is a continuous process of transferring low pressure fluid to the higher pressure side. These are also retrofits. They're also doing retrofits into the plants that RO reject actually recovers heat and puts it back into the system for at a high pressure to save on the pumping power. Of course, there's a link. I think you can share. I'll avoid it. Another thing is energy recovery turbines. So what they do is they put a turbine here. So whatever is the high pressure reject, actually, it rotates a pump. Is a turbine here, and that either you can have a HP pump. So you can have HP pump which is driven through the turbine or through the motor in case there is some problem here. So, or you can even generate power. You can put a generator, and you can have a synchronous generator which is feeding into the your inductive turbines, to the grid. So these are also available. Up to 1.5 megawatt they have done from a few kilowatts. So you see from 15 meter cube to 1200 meter cube per hour at this bar, they are able to do it. Then there are in water, especially for cross country, for units which are sucking water from the French wells in the river. There is a maybe 20 kilometer long pipeline of let's say 6 feet diameter is bringing it up. For example, in refinery or the petrochemicals here in Baroda, you will have this. So what happens is when this is pumping, ultimately it has go to a reservoir, which is just a gravity flow. So just before it goes to the gravity flow, they put the turbine so that all the pressure energy is recovered in generating power. And this is fed to the grid so that you save that much of. So in line, you are even have small generators. So these are all sort of push-in type of generator with the ceiling here. So no leakage takes place and you get power generation. Also in many of these lift irrigation schemes, etc., when you have high head and you don't need, so you don't have to throw the water. You just simply let the water fall, especially like in salt works. The water has to simply fall to the field. So there you can have, if the pressure are a little higher and the sea level is high, you can have back generation and feed it to your grid to save on power. There are some case studies. I'll give you an example. This is a typical case. It's a hot oil system, single pump hot oil system. This is a heater. Electric heater. So hot oil is pumped through the electric heater to the different process. These are all batch processes, and they have different requirement at a different point of time. Each of these pump is about 650 meter cube per hour. Now the requirement is these are all coal-fired heaters. So each one of them, you cannot reduce flow below 650. Least the oil will get degraded because the temperatures are bound to go higher. So you cannot afford. So they have a VFD on all this. I don't know for what reason, but VFD is running at full 50 hertz. So first thing we ask them is the VFD does not come free. So it's simply straight away bypass and start saving something because you're not controlling. You have to maintain 650 here. And so that was a loop. And most of the thing was coming back here because depending on the requirement here, whenever there's a control valve not operating, this control valve will open and bypass this. So this is how it was happening. So most of the hot oil was getting recirculated back into the system. What was the system done? We went in for a two-stage pumping. We have these pumps, actually, they pump through 650, but they do not develop that much pressure as much as was required. In this case, they were developing almost, because every pressure has to be developed only through this. So 6.5 kg, then whatever is overcome here, then whatever is overcome here, all has to be developed by this. So we split into a two system. This was 650 and 4.8 kg pressure. It passes through this. It comes at 2 kg is a loss across this. 3 kg here. So these are another set of pumps which are on VFD now. And that is a loop I was talking to you about. So that to maintain the equal distance. So you see in this, when it is going here, the return line is not taken like this. Return line is, so this is the longest path and equal path. And if you take this one, second line, so this will go here and then it will take this path and again long. So all paths are equal so that you don't have a problem of imbalances or unequal flow through all this. And whenever there's a lesser requirement of flow, there's VFD here which senses back pressure and it reduces the flow to this system as per the requirement. But here the requirement is 650 always. So what happens is here there's no VFD. It is simply circulating. So your head pressure has gone down, and accordingly, if you see, almost 119 kilowatt of power saving. This is almost close to about 95 lakh unit, and the modification pumps extra is another 70 lakh. So less than a year is the payback period. As another, exploiting the inherent. No, there was somebody who was buying RO water from outside the company. This was being put into the underground tank, and then you had two pumps supplying to all this. Now this line itself had enough pressure. So what we did was we kept the system as it is in idle and just put this piping modification. This line is feeding to all the systems directly to the inherent pressure in this line. So you don't have to discharge all the water here and then again pump it to a different system. Simply put this loops here. We left the system as it is because it was all investment was already done. But this additional investment was done. So whenever there is a pressure in the line is adequate, we are supplying through this. This is another distillation system. Again, what has happened is the condenser, because the distillation column is 16 meter long, this was almost at 20 meter height was the condenser, and all cooling water was going up to the condenser. Rest all system were at the ground floor only for this, and so was also for the chill water, because this is all low boiling solvents were being recovered. So they come here, and from after the condenser they go to a chill water. So they want to recover everything whatever is possible. So this was the system with very high requirement. Now what we did was simple. We changed this condenser. We brought it to the ground level. Chiller also we brought to the ground level. So now the cooling water pump requirement, which is much higher. Now we have to, of course, pump the reflex. But reflex pumping is much small quantity that you have to pump compared to the cooling water. The whole cooling water is a common system which is there. Second thing, what we did was when we brought it down, the first we whatever is the solvent which is coming at 30 degree, we had another reboiler installed. So this reboiler actually exchanges. It acts as a condenser first here. So it heats up and it preheats the reboiler. So it's a reboiler 2 is actually preheater to the existing reboiler 1. So your steam consumption will also come down. Your pumping requirement for both chill water and cooling water will also come down, and you save steam and power both. Almost 14 lakh was the saving per annum, and 10 lakh depending on the batch size, the number of batches that they were taking. This is another very typical in the process industry. We had a lot of, there's a lot of vibration taking place here. What is here is there's a reactor, actually a reactor bottom. The product is taken out here from the column at a defined rate. So this is maintained here. And what is done is to maintain this level, they are pumping in the neutralized mass is put in here at the section of these pumps. These pumps pump through the heat exchanger. There is a steam which is put in here, and then after heating it goes and gets flashed, and then how it is maintained here. So this level, as the level goes down, this operates. But what was happening is after every 2-3 days they had to stop this unit because there was a lot of scaling happening here. And these pumps, when they increase the pump, the lot of cavitation, because it's all thick mass slurry is happening here, because it is getting solidified because of the evaporation of the solvents. So this was actually vibrating. So they didn't know. They put a VFD, but with VFD, when they reduce the flow, a lot of scaling. So every 2 days they had to stop the plant. They had to clean up all this, and they were actually then they put a higher HP pump, and the problem did not solve. The problem further aggravated. But they were living with this. What we did was a simple solution. We put a pipeline here in a higher capacity pump, and higher capacity pump because the flow rates here have to increase so that there is no scaling taking place, and it will circulate at one point. It will keep on circulating here. Now because of this this backstream here, which is coming at a pressure, now there's no cavitation problem because NPSH available is now much better and simple solution. And now for last 6 months they have not had any cleaning being done in the heat exchanger. So simple addition to the pipe. Yeah, that is what I have written here. But anyway, another thing we did in a bitumen plant. See the bitumen filling in the tankers. Actually, there is a bitumen. This is a bitumen pump. Actually, it's a gear pump. So because bitumen viscosity is very high and the temperature has to be maintained at about 100 plus. So what they did was there was a bypass valve. Now, initially the bypass valve is open almost 150 meter cube is put back. And you know what is happening why in the bypass? Because when there is no, there are 16 filling stations here for the tankers, bitumen tankers. But they come at random, something will get filled up faster, somebody will later. So the back pressure will create. And there, of course, there is a pop-up valve because it's a positive displacement pump. There is a safety valve also here. But yes, to make sure that the safety valve doesn't pop up, they used to continue to maintain this as a recycle. Simple solution. We said nothing. Let's have a VFD here, which is now back pressure sensed. So it senses the back pressure. If the only two, let's say, tankers are filling up, the back pressure will create, and this will reduce the quantity here. And this was actually just as a safety margin 5% because they had a psycho. I said it is also not required, but they had a psycho. No, in case my VFD fails. I said VFD fails, then even motor will not run. But yes, they said no, but we want to have some safety, so we allowed them. Of course, there was a safety valve also, but so this is a simple solution. Put a VFD here and run it. But here there is no energy saving, but here tremendous energy saving. Of course, it is not in proportion to the affinity law. Here it will be just proportional to the flow. There were a lot of pneumatic valves. All these valves were pneumatic valves actually, whatever they had. So we said change over from pneumatic to, they have only 8 pneumatic valves. For that they had a compressor, which are, and a compressor, you know, is eats up 85% of the energy is already lost in the heat when you have a air compressor. So you know, there are now electrically operated MOVs are available, and you can put that even in you know, though they don't need a fire you know, proof area. But still, they insisted no. Sometimes solvents come and all that. So okay, that also is available. MOVs, electrical operated MOVs with the ATEX rating. Second thing was, you see, they don't see the see, there are control valves, but their control valves has two kind of you know, relays. Steady state. See here, standard relay. Normally L1, L2, when you do it, you take L1 you know, standard relay, because it's L1. Standard relays at 5.5 bar consumes 1.3 meter cube per hour. It is a continuous consumption. It has to bleed. It has to bleed whether it's operating or not operating, because it has to sense that yes, there is a compressed air. Otherwise, system failure will go to DCS. So it has to feed this. Now you see, they also have in a catalog low bleed valve. At 5.5, it is only consuming 0.18. What is the difference? 1.3 in 0.18. A tremendous amount of almost saving is possible through that. And these are things that one has to look forward. So with this, I end my presentation. And if there are any question answers, I'll be happy to address them if possible. Over to you, Bhavna.
That was so much informative, and like, it's not just theories and formulas, but practical experience that speaks and gives the results on the field can clearly be seen. And like, you have worked with so many emerging new technologies also, so really this will be very helpful. And there are a lot of questions today, and it was quite interesting. So let's take these questions. I'll just read out the questions, and you
Please
may
go ahead. Yeah. Please tell the name of the person and
organization name I won't be able to tell. I can see the name over here.
Okay, fine. Yeah.
So Mr. Balkrishna has a question. How do you take into account the increase in friction factor over the period of time while selecting the pump?
That's what I said. 10% margins are normally as a standard thumb rule. You have to keep that. And you're very right. Over a period of time, there'll be scaling happening in all the cooling water lines. There'll be, despite the fact that how much we are taking precautions. So one is you have to do liberal piping. There's nothing to do with the pump. Pump, yes, you already selected with 10% margins, but be little liberal in piping and MOC of the piping. Now that the new technologies are available, like CPVC, etc., wherever possible, you should try to put that.
Yeah.
Next.
Yeah, I hope that answers your question. Mr. Balkrishna, he has again another question. During pump selection, should the point be slightly on right side of best efficiency point?
It could be right or left. It's because both side it's immaterial. I said 80 to 110% is okay, fine. You can't be exactly on that, because once you start actually operating, you will find lot of things have changed what you had really contemplated during the design stage, and that you have to fine tune. Maybe you change impellers, or you do like what we have done. It was already designed running plant there where we have done some retrofits and try to improve the system. So right or left is the efficiency curves. If I just take you back on that,
yeah,
both sides efficiency curves go both sides. You see this 73 is, if you sing my cursor, this is 73. So you take here, you take here. From here to here is 73. From here to here, this is 74 region. Any point here will be 74. Any point here will be 73. Any point here will be 72. You get my point? Okay.
Yeah. Now the next question is from Mr. Said Mohammad Faik Raza. So his question is, when we convert constant speed pump to variable speed, what care should we take, or what study we should do so it doesn't affect efficiency and cavitation is avoided? What are the checklists when we convert constant to variable speed? I think that was discussed.
Yeah, I think constant to variable is fine wherever you have fluctuating flow requirements. VFD, I've even shared one of the cases here. And your next question is, actually when you put VFD, what happens is VFD is put to reduce the flow. You don't go beyond 50 hertz, right? It is always less than 50 hertz. So your RPM will reduce. And I said as flow will reduce. And the flow reduces, your NPSH required also is reduced. You get my point? I've shown you one curve, no? NPSH, actually all NPSHs are proportional to the flow. As flow increases, NPSH increases. Yeah. You see, as the flow is increasing, NPSH is increasing. So when you're talking of VFD, you will be coming in the back zone. You'll reduce. So NPSH required also will reduce, because everywhere flow will reduce. Once flow reduce, velocity reduce, your Reynolds number reduce, friction loss reduce. So everywhere there'll be reduction. So if you have no cavitation at 50 hertz, by putting VFD, be rest assured there'll be no cavitation, unless cavitation will not be there, but you have a problem of head, because many times people fail to understand this, that if your static head requirement is very high, as I told you, a VFD you cannot put everywhere. I think I showed you one curve. Yeah. If the system curve is like this, which static requirement is almost flat, then putting VFD will actually, your pump will be rotating, you will not have adequate water at the top. So that you have to take care of. Okay. Anything else?
Yeah. Next question. His next question is, can we use axial field integral motor pumping system in chilled water line?
Chilled water line is very good, because you need cooling. Motor will be cooled, very good cooled motor. Higher temperatures you cannot have, because the insulation issues will come. And these are all actually, permanent magnet motors. So low temperature is not an issue. High temperature will be an issue.
Yeah. So the next question is from Mr. Kashif Shabir. Have you done any energy saving project in wastewater treatment? What are the area need to see for energy saving except blowers and pump operation?
Except blower and pump operation. Oh my
Yeah.
God, it's a huge field. When you say wastewater treatment, it's a huge field. Actually, you can convert a lot of your CO2 into methane.
Mhm.
Bioreactors you can put. So you can generate energy. Now those days are gone that you treat and then waste it. But it depends. What is the composition? How much is the organic compound that you have in the... So, I mean, it's a very detailed subject by itself. And you said already you have removed the pump and a blower. So where is the energy?
Mhm.
Energy is only in these two places. Either you have aeration in the aerobic treatment, or you have pump, which is pumping the thing. So other than these two, where is the energy? I don't understand your point.
Yeah, I think they'll have to share. Mr. Kashif,
You have my email ID. You can write to me if
yes,
anything
yeah,
specific.
you can discuss by email, or you can even convey us the questions and we can communicate to you. Mr. Kashif, we will be sharing the complete presentation on our LinkedIn page of AEEWI Western India chapter, and you can see the slides there. Right. And another question is from Mr. Sharma, C. Sharma. Efficiency curves are almost flat at range of ends. Should the pumps be designed in that ends range where efficiencies are almost constant? When NS increases, efficiency decreases a little from the best efficiency. Please suggest.
No, I didn't quite get your question. Actually, you're saying pump efficiency you're talking about, or your axial flow? You're talking of axial flow, right? I
I think I'll allow him to talk. Just one sec. I'll allow him to talk.
Is this what you're talking about?
Yeah, Mr. Sharma, you can now talk.
Hello?
Yeah. Yes,
See,
Mr. Sharma. Yeah.
Yes. Yes, Som sir, can you please refer the x-axis where the x-axis represents the specific speed of a pump, and once you see the can you please go back to this slide?
curve?
Yes, this one. No, not the previous one.
This one?
Yes, this one. On the y-axis, you are showing the efficiency.
In
So,
percentage. Efficiency in percentage.
yes.
Whatever is the efficiency, percentage of that.
Yes. And for different flows, you are giving the curves for the efficiency. So, considering the, say, the 10,000 GPM curve, it is the efficiency is constant in between the 2,000 to 3,000 specific speed, right?
This one, this 10,000, this,
Yes.
this 10,000.
10,000 GPM.
This 10,000 GPM.
The efficiency is maximum in between 2,000 to 3,000.
Yes. Exactly. Yes.
So when the specific speed increases, the flow remains constant 10,000 GPM. The efficiency drops.
No. See, the specific speed increases. 10,000 GPM is constant, but specific speed is to decide on the shape of the pump.
Okay.
Shape of the impeller actually, and the pump casing. So actually, every manufacturer, see, nobody designs a pump for your application. They have a set of model 1, 2, 3, 4, 5. or you want model 1.1, nobody will give you. You have
Yeah.
to take either model 1 or you have to take model 2. Nobody does this kind of a detailing for specific to your needs.
Okay.
So you have to either choose pump 2, for which they will give you a curve, or you have to choose pump 1, which is what meets your requirement. But they may be slightly deviating from what is your specific need.
Yeah.
Okay.
Okay. Thank you.
Thank you.
Thank you. Mr. Balkrishna, you have anything further? Any further question? You may ask. You are allowed to talk. You may unmute your mic and talk.
Hello.
Yeah.
Yes.
Sir, my previous question regarding where the design, the point which is selected, it should be, books say that it should be on the right-hand side of the best efficiency point, because with the deterioration over time, the point would align towards the best efficiency. So I was asking that question.
Okay. So either side. I mean, I'm just saying, you see the efficiency curves. See,
Yeah,
efficiency
no, but
curves.
but
They
if
are
it on the
they're like, oh, the 73 curve is like this. Now, what is left, what is right, I don't know. What do you mean by this?
But if you
Anything
select
which,
on the left-hand side, sir, what will happen over a period of time when the system head increases because of the deterioration in the pipeline, the efficiency would drop further.
No.
you're trying to say system curve is okay.
Yeah.
Oh, let me come to the system curve. Okay. We had
Because
one.
system curve would move to the right-hand side.
Yeah.
To the left-hand side. To the left-hand side over a period of time. It will become more steep.
Yes. Your head requirement will increase over a period of time.
Increase over a period of time.
Yeah. You're right. Yeah. This is the example.
Yeah. So
So
if you
you're
select,
you select this point over a period
yeah,
of time, it will go here.
yeah, if
And
you select on the right-hand side,
if
over
you're
a period,
yeah, you're right. Absolutely. This is the typical performance curve. Black one is what will happen after, let's say, 5 years.
yeah.
So that's okay. You can select this side, or if it is
Right-hand side is actually advisable. Right-hand side of the best.
yeah, absolutely.
Yeah, sir. My second question was, when the design point is can be the pump can be steep characteristic or flat characteristic. So which is advisable? Does the variation in system head and the variation in discharge make this in this decision making?
No,
Meaning
the
we can use,
control point. See, whatever is your system requirement has to be met through that pump. But if you are having a control mechanism, that is where I think I had shown you this curve. Yeah, this curve. If it is a flatter, the system is flatter, then yes, VFD will not work because the head will not be developed as much as you need. Head will fall in the square proportion.
sir, my question was without VFD, if we have to select either a flat head or a steep characteristic or a flat characteristic, which we should go for?
Go for a steeper. Pump side. Pump wise, you should go for a steeper.
Steep characteristic, because it is higher efficiency. Centrifugal are higher efficiency.
Yes.
Okay.
Okay.
Sir, thank you. Yeah.
Okay.
Yeah. Hope that answers all the questions. And if you have further questions, you may contact Mr. Derashree directly, or you can write a mail to us, and we will be happy to forward it to him. And
I'll leave my contact details. Just one sec.
yeah, please.
Sir, one last question I had. Last question, please. Now, in spite of using VFD, you said the advantage of is only 2.7% something. How that's so much of reduction is there? 2.67.
Actually, practically, this is theoretical. Theoretical is cubic proportion. But theory never works because there are a lot of other things which are happening. For example, even VFD, the lower you go, the higher consumption within the VFD itself. VFD
Yes,
also has
yes.
IGBTs, no? They also
Yeah,
consume energy. VFD does not come free.
correct.
So the lower the RPM you take, more the consumption in VFD also.
Yes, sir.
So all those put together, practically, this is a figure I have taken from a US, DOE. This 2.67 is a practical figure, because cubic proportion, if you give, you will give very, inflated
19%.
savings.
19% it is coming.
Huh. Okay.
Okay. So thank you
Anything
very much.
else?
Thank you.
Okay, fine.
Yeah, I have given the link in the chat box, so where you will see the presentations. By Monday maximum, it will be available. These presentations will be available there in the form of recording.
And I have given a disclaimer here because a lot of charts, drawings
Yeah.
I have taken from net.
Yeah.
But it is only for the purpose of education. This is a free education to everybody. So academic use. That's why I thought it's better. It explains things much better than simply talking.
Very much.
Okay.
Okay. Thank you so much, Mr. Derashree. It was great to have you on this forum. And one more thing that I have missed in your introduction is that you are award recipient from AEEWI, that is the Energy Engineer of the Year, and also Hall of Fame Award. So it's really privileged to have you here. And we hope to continue this association with you in future also.
It'll be
And
pleasure, definitely.
all the participants for being here. And this is almost, we are end of this year, but definitely we will try our best to keep continuing this journey of our webinar series next year also.
What is the total number of participants?
Number of participants total was around 40. I'll be sharing you the list. Thank you so much.
Okay, thank you very much. And happy Diwali to everybody once again. Thank you.
Happy Diwali to all.
Happy Diwali.